Hello, my name is Andrew Carratu. I'm a teaching assistant at MathTopia Academy, and this is the 2023 AMC 8 problems 15 through 25. So this is the 2023 AMC 8 problem number 15. So Viswam walks half a mile to get to school each day. His route consists of 10 city blocks of equal length, and he takes 1 minute to walk each block. Today, after walking 5 blocks, Viswam discovers that he has to make a detour, walking 3 blocks of equal length instead of 1 block to reach the next corner. From the next time he starts his detour, at what speed in miles per hour must Viswam walk in order to arrive at school at his usual time? Okay, so let's just calculate how long it takes for him to walk each block first, and we can go from there. So, because the final answer is not asking just for how much faster he has to walk, but actually what speed he has to walk in miles per hour. So he walks half a mile, he walks 10 blocks, which means that each block is a 20th of a mile, and he takes 1 minute to walk each block. So 1 minute to walk each block, and each block is a total of a 20th of a mile, right? Which means if we want to convert this into miles per hour, we need to multiply both by 60. So multiplying this by 60 gives us 1 hour, and this gives us 3 miles, which means that for every 1 hour he walks 3 miles. So that means he's walking at a speed of 3 miles per hour. Okay, so the question is, if he takes this detour, right? From the time he starts his detour, when does he start this detour? Well, he clearly starts it here, right? That's when he first can't go his normal way. He has to go around. So the question is, how much faster does he have to walk? Well, normally he walks 1, 2, 3, 4, 5 block lengths, right? But now that he has to take this detour, he's walking an extra 2, right? 1 to go up and 1 to go back down, right? So he's going 1, 2, 3, 4, 5, 6, 7 blocks, right? So he wants to arrive at his usual time. So clearly he has to walk 7/5 times faster, right? Because if he normally walks right at 3 miles per hour, he's going to have to walk 7/5 times faster to walk 7/5 as many blocks. That's because it's a simple ratio. So we just have to multiply this by the miles per hour he normally walks at, and that gives us 21 divided by 5, which we calculate to be 4.2 miles per hour, and that's answer choice B. Okay, this is 2023 AMC 8, problem number 16. The letters P, Q, and R are entered into a 20 by 20 table. According to the pattern shown, how many P's, Q's, and R's will appear in the completed table? Okay, so this can get a bit confusing, but we can try to think about this with, we can just try to think about this as a sum. So let's just ignore the Q's and the R's, right? And let's look at how the P's look, right? So let's just ignore the Q's and R's, right? So where are the P's? The P's are this square, this diagonal, right? It's not completely drawn in, but we know it's this diagonal, right? And it just repeats like that. P, 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 P. And clearly, since we're moving over by 3 each time, the diagonal gets longer by 3 each time. So to count the number of P's, we just add 1, then add 4, then add 7, and so on. But there's a place where we stop because the table kind of cuts off, and that'll cut us off. We won't keep it increasing by 3 forever. So the question is, where does this happen? Well, let's think about it, right? Let's look at this top corner here, how that would look. Well, here's the thing. We write P in the first square, the fourth square, the seventh square. Eventually, we keep writing stuff that is 1 in remainder 3, right? So eventually we're going to reach, well, 1 above 18, which is a multiple of 3. So we're going to write a P right here, right? And we're going to have a diagonal here, which is in the 19 square. And following this trend of it being in the square number in the first square, it's of length 1. In the fourth square, it's of length 4. In the seventh square, it's of length 7. So clearly, in this 19th square here, it's going to be of length 19. So we know where we're going to stop. But the thing is, it keeps going, right? It doesn't stop there, but it just decreases now because, as you'll see, right? Well, we're going to have like q's here. We're going to have like a diagonal of q's here. We're going to have a diagonal of r's here. We don't need to worry about that for now. And then we're going to have a p here. And this numbering we applied up this edge is going to apply here as well, except we start numbering from the corner over here, right? Numbering the squares 1, 2, 3 across like that. And we would reach 18 here, right? And clearly that means we're going to have a diagonal of 18 here, right? Which makes sense, right? Because this is diagonal of 19. This is the longest diagonal of the board, which has length 20, then 19, and then 18, right? So that makes sense. So we're going to have exactly 18. And then what's going to happen next? Well, now we're going down this way, which is actually decreasing the length of the diagonal by 3 each time. So we're just going to keep adding down like that until we reach 3. So what does this sum equal? Well, we can just use simple sum of an arithmetic sequence of some amount of terms, right? So we can just split it up into 2 sequences, right? This first sequence has sum of first and last terms 20. How many terms are there in the sequence? Well, we can count 1, 4, 7, 10, 13, 16, 19. That's a total of 7 terms in this sequence. And then we divide by 2. And what about this? Well, the first last terms add up to 21. There's 6 terms in the sequence, divide by 2. And this gives us our total number of p's, which is just going to be, well, this is 70. This is going to give us 63. So we have a total of 133 p's. So that eliminates a lot of choices. We're down to these 2. So the question is, which of these, right? But now, actually, because we've done it once already, it's not going to be too hard to do it again. So let's just do it again for Q, right? And we can do it a lot faster this time because we know what we're looking for. So, well, what is the first diagonal? Well, this is, of course, 2. What is this diagonal? This is 5. What is this diagonal? Well, we know it'd be 8, and it would keep increasing like this. And then notice now we're hitting a 2 in mod 3, right? So we're going to end up hitting 20 actually, which makes sense because in this diagram we already drew these q's here, which makes sense. Q is taking up the longest diagonal, which means it goes up to 20, and then it just goes down again, right? Q 17. So it's actually going down with the exact same numbers that I came up with, which is interesting, right? So we go 17, we go 14, we go all the way back down to 2, just like that. So now, how much does this sum equal? How much does this sum equal? We can look through, well, this is 22. How many terms are there in the sequence? 7, divide by 2. With this one, it's similar, except the first and last terms at the 19. There's only 6 terms in the sequence, and we divide by 2. So this adds up to a total of 57. This adds up to a total of 77. We add those up, we get a total of 120 plus 14, 134 q's, which means 134 q's, 133 p's. We can simply subtract to obtain that there are 133 r's, and that makes our answer C. Okay, so this is the 2023 AMC 8 problem number 17. So a regular octahedron has 8 equilateral triangle faces with 4 faces meeting at each vertex. June will make the regular octahedron shown on the right by folding the piece of paper shown on the left. Which numbered face will end up to the right of Q? Okay, so this can be pretty hard to visualize in 3D, but there's a pretty simple way that we can go about this in a way that we don't have to worry about accidentally messing up, and we don't even have to like try to visualize anything in 3D. We can just so the problem is that we have this net that represents what this octahedron would be when it's folded together. But the problem is that it's pretty easy to see that this Q is this Q, right? This 6 face goes to the left of it. This 7 face goes over here. But the question is what face goes over here, but we know it's going to have to be somewhere over here because it's going to have to be one of these because there's nothing else to the right here, right? So the thing is, what we can do is we can simply track an edge. So what we want to do is we want to, our goal is to track a path that goes around the figure in a way that we will return back on the other side. It's going to look something like this, right? And once we reach the other side, we're going to be able to figure out what the face is. Okay, so let's start doing that. So first we draw this red edge here, right? So what does that edge represent in the surface net? Well, that just represents this edge right here, right? And so then we draw this line right here. Well, what line does that represent? Well, let's think about it. There's a junction here of 3 triangles, but we are turning in a way that creates this angle of 1 triangle here, which we know has to go along the path in this way, right? Then we go along this line right here. Well, this line splits it, 2 triangles are above it and 2 triangles below it, right? So we know that this line here has to represent this line. It also represents this line because we know the surface net's going to connect along here, but we're going to continue following the path along here because that's what's going to get us closer to our answer. Well, now, what about this line? What does this line represent in the diagram? Well, once again, this yellow-green line, right? It has 2 triangles above it, 2 triangles below it, right? So we don't want to draw it like that. That would create 3 triangles in one partition. So we want to draw it like that, right? So now we've gotten to this edge and now we're very close. So now the final step is just, well, we're going up like this. And well, that clearly is going up like this. So now the question is, what is this question mark side? And at this point, it is very clear that it's this. It's the face that has the blue and the green edge in that manner, which means that it's going to be face number 1. Okay, this is the AMC 8 2023 problem number 18. Greta Grasshopper sits on a long line of lily pads in a pond. From any lily pad, Greta can jump 5 pads to the right or 3 pads to the left. What is the fewest number of jumps Greta must make to reach a lily pad located 2023 pads to the right of her starting position? Okay, so we have this grasshopper and she's trying to hop. So the thing is, this problem, these kinds of problems would be very difficult, but this one's actually not too bad because the thing is, Greta only has 1 way to move right and 1 way to move left. So if she wants to move right, she only has 1 option. If she wants to move left, she only has 1 option. And she actually, because she has only 2 hops, what we can do is we can say, well, let's say she has a series of hops that represents the fewest jumps possible, right? She might jump 5, 3, 5, 5, 3, doesn't matter how she jumps, right? Well, what we can do is we can just rearrange her jumps in a way that she does all the 5 jumps in the path first, right? However many she does. And then she does all the 3 jumps in the path next and ends. And the thing is, of course, because we're just adding, because the representation of a path is just a sequence of adding 5s and -3s in some order, like, for example, like this. So, of course, if we're rearranging it so that we add all the 5s first and then add the -3s, right? By the commutative property of addition, we're not going to change the final result. So basically, what we're saying here is we can simplify the problem by a lot by saying that all we need to care about is first she jumps some amount to the right, 5 jumps, and then she jumps 3 jumps. So let's think about that. How many 5 jumps could she possibly do? Well, let's say the number of 5 jumps she does is, well, the thing is, she has to do enough 5 jumps to be at least over 2023 pads. So she has to be like over 23 pads. She has to at least overshoot it. And the reason for this is simple. Once she stops moving to the right, she can only move to the left. So if she hasn't reached 2023 yet, she's never going to reach it by going to the left. So well, the minimum she can reach is 2025 by jumping a total of 405 times with the 5 paths to the right. But the problem is if we start jumping left here, we're going to run into a problem, which is that because we are only jumping 3 paths at a time, we instantly jump over our target. We instantly jump over it. So that doesn't work. Well, now the question is, what if she jumps another hop, right? So 405, that clearly doesn't work. What happens if she jumps 406? Well, that brings her to 2030. But if she tries to jump left here, she'll also end up skipping over 2023. She'll go 2027, 2024, and then 2021, and she'll have jumped over it. So 406 doesn't work either. So 407, as you might expect, because we've had 2 failed results, and this is the 3rd. So as you might expect, this one does work. So 407, if we jump that many times, we end up going to 2035, and then she can jump a total of 4 times back, right? 2032, 2029, 2026, and then 2023, and she lands on the right lily pad after a total of 407 plus 4, 411 hops. But the question is that the correct answer? How do we know that this is the correct answer? Well, let's think about it, right? If we keep going up, right, eventually, once we reach a total of 408 hops, for example, we'll run into a problem, which is that we will never be able to get a smaller jump count, right? So let's think about that, right? If we jump greater than 407 times, then we're going to end up at a number greater than 2035, which is going to require greater than 4 hops to get back to 2023, no matter what, which means that greater than 407, greater than 4, means that we're always going to take more than 411 hops if we use more than 407 hops to the right, which implies that 411 is our minimum because, well, there's simply no other sequence of hops that can achieve anything lower. So that's our answer. Okay, this is the 2023 AMC 8 problem number 19. An equilateral triangle is placed inside a larger equilateral triangle so that the region between them can be divided into 3 congruent trapezoids, as shown below. This one. The side length of the inner triangle is 2/3 the side length of the larger triangle. What is the ratio of the area of one trapezoid to the area of the inner triangle? Okay. Well, the thing is, what we should focus on is the fact that, well, let's think about it. What happens if we found the ratio of the smaller triangle to the area of all of this space, right? What if we found the area to that black region on the inside to this whole red region here? Well, from there, it wouldn't be too hard to get our answer, right? If we had that the ratio of the black region to the red region, right? Well, our answer is just whatever this ratio is, right? Well, we're actually looking for the ratio of red to black. We're looking for the ratio of red area to black area, and then at the end we can just multiply by 1/3, right? So because if we're looking for just the area of one of the trapezoids instead of the 3 congruent ones, right, we just multiply by 1/3 because the numerator will be 1/3 of what it is. So now our goal just becomes finding what this ratio is, but this ratio isn't too hard to find because this is this ratio is just equal to 1 minus the ratio of the smaller triangle to the bigger triangle. Or actually, it's more complicated than that, but it's actually the ratio of the bigger triangle to the smaller triangle minus 1, right? But the thing is, because equilateral triangles are similar, right? And the ratio of these side lengths here are 2 to 3, right? Let me erase these drawings here. Because the ratios are in some ratio like 2 to 3, we know that the ratio of the areas has to be 2 to 3 squared, so 4/9, which means that if we say that the area of the big equilateral triangle here, if we say that that area is 1, the area inside here is 4/9, and the area in this region here is just 5/9, right? And as we've said before, we're just looking for this this was the red region, and we just want to divide it by 3. So 5/9, and then we divide it by 3 to get 5/27. And now we're just dividing this by the black region that we wanted, 4/9. And now we can just simplify the fraction, multiply both sides by 27, 5/12. That gives us our answer C. Okay, this is the 2023 AMC 8 problem number 20. Two integers are inserted into the list 3, 3, 8, 11, 28 to double its range. The mode and median remain unchanged. What is the maximum possible sum of the two additional numbers? Okay, so let's think. Let's call these two numbers that we're adding to the list A and B, right? Well, let's think. What happens if we were to, how could we double its range, right? Well, of course, we could double its range from the top by making this, well, let's think. This range currently is 25. We want to double it. We'd make the range 50, which means we'd want the bigger number to be 53, right? Alternatively, we could extend it from the bottom, but the thing is, it seems like doing so would be a bad idea because we're making a lower number, right? So let's try to rigorously show that we want to have 53 be the larger of our numbers, right? So let's say A less than or equal to B, right? So these are the two numbers we're adding to the list. So really the main thing we have to worry about, other than the fact that we need to double its range, is the median part, right? The mode part is going to come into place one time, but it's really not that hard to change the number that causes the confliction to not be equal to any of the numbers in the list, right? Because, well, we have a mode of 3 here. We have 2 3s. We need to keep the mode as 3, right? If we have another number, for example, if we had like A equals 11, that would cause the mode to be multiple numbers, which is not the equivalent of the mode being one number. So that counts as it changing. So we need the mode, we need the median to stay the same. So we can't just have both of the numbers be greater than 8 because that would make the median no longer 8, right? We would have the lowest 3 numbers in the list be 3, 3, 8, and there would be 7 numbers in the list, and the other 4, these 4, would all be greater than 8. So the median could no longer possibly be 8, which means that this could not happen, which means A is less than or equal to 8. Well, what could A be then? Well, it can't be 8 because, like we said, this is the one time it comes into place, the mode. That would cause a confliction. It cannot be 8, so we could try to make A 7, right? Well, now we just need to maximize what B is. And the way we maximize that is, of course, we do what we mentioned before, which is by making B 53 and doubling the range. And this gives us a sum of 53 plus 7 is 60. And the thing is, we cannot do any better than this. Why? Well, because the maximum number we could ever choose for B is 53. If we ever made B more than 53, that would definitely make the range larger than 50, because we would always have a 3 here at the end of the list as the bottom, right? We cannot somehow make B greater than 53 and keep the range at just 50. That's not possible. And as we previously mentioned, A cannot exceed 8, right? And it has to stay at 7, right? Because A simply cannot be greater than 8. It cannot be equal to 8. It causes a contradiction. So A just has to be equal to 7. So the maximum value A can obtain is 7, and the maximum value B can obtain is 53, which means the maximum value they can obtain together is 60. So we cannot do any better than that, and our answer is D. Okay, this is the 2023 AMC 8 problem number 21. Alina writes the numbers 1 through 9 on separate cards, one number per card. She wishes to divide the cards into 3 groups of 3 cards so that the sum of the numbers in each group will be the same. And how many ways can this be done? All right, so let's think about, well, what's the total sum of all 9 cards, right? This is pretty simply, we just, use the formula for sum of first n numbers. It's just 45. So if we're going to divide 3 groups of 3 cards so that the sum is the same in each group, we of course need the sum in each group to be 45 divided by 3, 15. So we need the sum in each group to be 15. So now we can think about this on a case-by-case basis. Of course, there has to be a group with the card labeled 1 in it, right? We can't just discard 1. We're using all 9 cards. So now the question is, how many ways can we make the group with 1, right? Well, let's think. Well, we could choose 1, 5, and 9. We could choose potentially 1, 6, and 8, or we could choose 1, 7, or we can't choose 1, 7, and 10. My bad. Yes. Because that would use 2 cards 7. We do not have 2 cards 7. So these are our only 2 possibilities. So the question is, given these 2 initial groups, how many ways are there to create the other 2 groups? Well, of course, there also has to be a group with the number 2 in it, right? Because we're using all the cards, there's a card label 2. So how many ways are there to create a group that adds up to 15 that includes 2? And we have to keep in mind that we cannot repeat any numbers from above because we only have 1 of each card. So let's think, how many ways are there, like ignoring these groups and it conflicting? How many ways are there? Well, we could try 2, 4, 9. Really, because this is 2, we need these 2 numbers to add up to 13, which can be done with 4, 9, 5, 8, or 6, 7. Those are only 3 ways, right? And because, no, the problem is considering just groups. It's considering 3 groups, so we just assume that the groups are just, well, it's just 3 cards, right? We don't have to worry about the order of the cards in each group or the order of the groups, right? So that's why I'm just writing them in least to greatest order. So it's just these 3. These are the only 3 possibilities. So let's think about over here, 1, 5, 9. This creates a contradiction with this group and this group, right? We have a repeat 5 here, we have a repeat 9 there, which means our only possibility is 2, 6, 7. Well, now what can the final group be? Well, it's pretty easy. It's just the 3 numbers we have left. And because of the way we've calculated, right, we know the sum of the numbers. The sum of the numbers from 1 to 9 is always 45. So if we make the first 2 groups sum to 15, the last group will always sum to 15. And we can see that here. And that gives us our first possibility for how Alina could divide the numbers. And the second case, well, what contradictions does 168 cause with these 3 groups? Well, causes it with the second one and the third one. A repeat of 8, a repeat of 6, which means 249 is our only possibility, which means our final group must have the numbers 3, 5, and 7. And that is simply our only other way to do it. And we're done. There's only 2 ways that we can pick the 3 groups. Our answer is C. Okay, this is the 2023 AMC 8, problem number 22. In the sequence of positive integers, each term after the second is the product of the previous 2 terms. The 6th term in the sequence is 4,000. What is the first term? Okay, so to solve this problem, what we need to do is we need to create variables to represent these positive integers. So notice that we just need to define the first 2 terms, and then after that, all the other terms in the sequence are defined. So let's do that. Let's write down the numbers A and B, and now let's just write out the sequence. A, B, the next one would be A times B. The next one would be A times B, AB squared. The next one, well, we'd have A times A squared, B times B squared, B cubed, right? And then the 6th number, which is what we're looking for, A times A squared, A cubed, and B squared. Oh, sorry, that looks like a 3. Let me rewrite those. B squared, B cubed. B squared times B cubed gives us B to the power of 5. And we know this has to equal 4,000. Well, how does this factorize? Because prime factorization is very important for us understanding what values A and B could take on. Well, 2 to the power of 5 times 5 cubed. That's the prime factorization. And we can get this pretty easily because, well, we know that 10 is 2 times 5, and this is just 4 times 10 cubed. So it's just 2 cubed times 5 cubed times 2 squared. So 2 to the 5th times 5 cubed. So it's pretty clear here that there's a very obvious solution of b equals 2 and a equals 5. But how do we know that's the only solution? Well, that's where the fact that they're positive integers comes into play. What positive integers could b take on, for example? Well, there's only 2. It could only be 1 or 2. Because if it were anything else, if it had any other prime in its prime factorization, like let's say it was 7, of course, 7 to the 5 is not a part of this, right? So it can only be these two. And if it were 1, notice that a would have to be the cube root of this whole number, but 2 to the 5 is not a perfect cube, so we get an irrational number, which is not a positive integer. So basically what we're showing is that the only way to split it up is the obvious way, which is a is 5 to account for 5 cubed, and b is 2 to account for 2 to the 5, and that gives our first number here as 5. That's our answer, T. Okay, this is the 2023 AMC 8, problem number 23. Each square in a 3x3 grid is randomly filled with one of the 4 gray and white tiles shown below on the right. What is the probability that the tiling will contain a large gray diamond in one of the smaller 2x2 grids? Below is an example of such tiling. So, large gray diamond, that is clearly talking about this shape right here. So, how could the shape appear in the grid? Well, there's 4 ways it could appear in the grid. It could appear in the top left. It could appear in the top right. It could appear in the bottom left. Or it could appear in the bottom right. Those are our only 4 ways that it could appear. So the question is, let's think about this. Could we have more than one diamond in the grid at the same time? Because if so, then we can't just count each of these events happening individually, right? Like if they are all independent events, we can just calculate the probability for each of them and add them up. But is there a way that they could happen together? Well, no, because note that this middle square here, depending on what the diamond is, if it's in the top left, it must be this square. If it's in the top right, if you'll notice, it has to be this square. If it's in the bottom left, it has to be the square. And if it's in the bottom right, it has to be the square. There's simply no other way. So basically, because each of these 4 only happens based on what this tile is, right? Only one of them can happen at once. So we can just calculate the probability that one of them appears, plus the probability the second one appears, plus the probability the third one appears, plus the probability the fourth one appears. But it's clear that this problem has a sort of rotational symmetry to it, right? Because each of these tiles can take on any of the 4 directions. So for example, for any case we have with a gray diamond here, we could get a case for the top right diamond by simply rotating it 90 degrees. So basically what the point here is that all we need to do to solve the problem is find the probability that this diamond appears and then multiply by 4, because the probability of any of the other diamonds appearing is exactly the same, and these are all independent events. So now we get to the actual part of finding the probability, which is very easy, because this square, what is the odds of it facing this way? Well, there's 4 tiles. It's choosing at random, 1 out of 4. What is the odds of this tile facing the right way? That's 1 out of 4. What is the odds of this tile facing the right way? That's a 1 out of 4. What is the odds of this tile facing the right way? That's 1 out of 4. And we have a total of 4 diamonds, and we can just multiply by that because, yeah, because the probabilities are each independent. So this product here, what does that equal? The 1/4 and 4 here cancel, and we just get 1 over 4 cubed, which is 1 over 64, and our answer is C. Okay, so this is the 2023 AMC 8, problem number 24. Isosceles triangle ABC has equal side lengths AB and BC. In the figures below, segments are drawn parallel to AC so that the shaded portions of ABC have the same area. The heights of the two unshaded portions are 11 and 5 units respectively. What is the height H of a triangle ABC? Okay, so let's think about how we can find the fact that these are the same area, because clearly these two having the same area clearly creates a relationship in H. The main issue is we don't know anything about the actual area of ABC. And we don't know anything about the side lengths of ABC either. And actually, the side lengths could really be anything. We could really have ABC as we could have it be this large, or we could have it be this skinny. It would really not change the problem at all. So we have to set a variable as the area of the triangle. I'm going to say that the area of ABC is K. Okay, well, now how can we use this to find the area of this trapezoid in terms of K? Well, the answer is similar triangles, specifically because we say AC and this line are parallel, right? We know that these angles are congruent, and we know that these angles are congruent, right? And we know this angle up here is congruent, right? So we have similar triangles, right? By angle similarity. So this triangle here is similar to this big triangle, ABC. So the thing is, when two triangles are similar, right, we know that the ratio of their areas is equal to the square of the ratio of a special length. So that length can be a side length, it can be angle bisector, it can be perpendicular bisector, or in this case, it can be an altitude. So the ratio of the area of this smaller triangle to the bigger triangle ABC, which I'll just use this triangle just to have it here, right? The ratio of 11 to H squared. And don't forget to multiply by K. So this is what the area of this tiny triangle is. Well then, what is the area of this trapezoid? Well, we can just subtract from K. Furthermore, we can factor out the K, like this. Just delete the product sign. And this is what our area of the trapezoid is. Now we move on to what's actually the easier case. First off, we know that this altitude here of the smaller triangle is H minus 5. And now we apply the exact same logic as we did before, which is that the area of the smaller triangle must be the square of what we like to call a scale factor, H minus 5 over H, the ratio of the altitudes, squared times K. So we have found the area of both of these shaded regions, at least in terms of what the area of the full triangle is. But how does this help? Well, we look back at the problem, we've pretty much solved it, because we have an equation with only H in it, and these K's will immediately cancel when we set them equal to each other, because we can set them equal to each other because these shaded portions we chose have the same area. So we just set these equal to each other. So, like I just said, cancel out the K's, and now we see why the shape of triangle ABC doesn't actually matter for this problem. And now we just have an equation with H. So we can simply solve it. So let's, first off, this ends up being, if we expand the square root here, we get 121 over H squared. And if we expand the bottom part, we can actually just expand the whole thing right now. H squared minus 10H plus 25 on the top, and on the bottom we get H squared. So now we want to multiply both sides by H squared. Get all that nice canceling. And now we get even more nice canceling, in that this H squared here cancels out with this H squared here. Remember, this is a negative 121. And now we move the negative 10H to this side, 10H. We move the negative 121 to this side, 121 plus 25, 146. And we simply get H equals 146 over 10, which is equal to 14.6. And that is choice A. Okay, This is the 2023 AMC 8 problem number 25. 15 integers, A1, A2, A3, all the way up to A15 are arranged in order on a number line. The integers are equally spaced and have the property that A1 is somewhere in between 1 and 10, A2 somewhere in between 13 and 20, and A15 somewhere in between 241 and 250. What is the sum of the digits of A14? Okay, so this problem's a bit daunting and confusing because it seems like there isn't just one list of integers that meets these conditions, but in fact, as we will show, there is exactly one sequence of integers, A1 through A15, that meets these conditions. And the reason why is because it is very hard to set A1 and A2 such that when we create our numbers A3, A4, A5, all the way up to A15 will be exactly in this range. It's hard to get in this range. So, well, the thing is, what exactly is it talking about that they're arranged in order on a number line and that they are equally spaced? Well, this is simply just another definition for an arithmetic sequence, right? So let's just set A1 equal to our initial value A, and we'll let the difference, the common difference between any two numbers, let's just let that be D. So our numbers go A plus D, A plus 2D, right? And so on, all the way up to A plus 14D, which we know is A15. And we know that 241 less than or equal to A plus 14D less than or equal to 250. So how do we use this to figure out what exactly our numbers are? Well, we have our bound for A. We know exactly where A lies in between. A is just A1. So we know that A lies in between 1 and 10. But where does D lie? Like, can we create a bounding for D? The answer is very easily yes, because we know, as we have just clarified, A2 minus A1 is D. So what values can D take on? Well, at maximum, this is when we take the maximum of 8 for A2 and the minimum for A1, which is 20 minus 1, which is 19. And the minimum value for D is 13 minus 10. 13 minus 10 is 3. So we have successfully created our bounds for D. 3 less than or equal to D less than or equal to 19. So if we try, for example, D equals 3, we're not going to get very far, right? A plus 42, we have to get to 250, and A can be at most 10. We're not getting very far. Clearly, D has to be very large. So it's a much better idea to try values of D from 19 and going down. So let's try our value of D equals 19. Well, 14 times 19, if we do this multiplication here, we get 100, 130, 36. We add those up, we get, 100 plus 40 plus 90 plus 36. We just get 266, which exceeds 250 already, and A can't be negative, so we've already failed. So that doesn't work. What about D equals 18? 14 times 18, if we do this multiplication, we get a total of 252. Once again, just barely too much. So that doesn't work either. And now we get to D equals 17. This is where it's interesting. Well, if we try D equals 17, 14 times 17 actually gets us a bit short. If we multiply this out, we get a total of 238. This isn't enough. So is this problem impossible? Well, the answer is no, because remember, we are adding A onto it, right? And A can be in between 1 and 10. So A couldn't be negative. So if we were too much, we couldn't get into the bounds. But if we're too little, in this case, for example, we actually can get into the bounds. But we actually have to be really careful because there's only a handful of pairs of numbers, A1, A2, such that their difference is actually 17. There's actually not that many numbers that satisfy that, right? For example, if we just went ahead and picked, A equals 7, well, that brings us to 245. That's in the bounds. But the maximum that D could be at this point, we could only choose D equals 20. And then 20 minus 7 is 13. And we didn't get our 17 value that we need. So clearly we can see already that we need A to be at most 3, right? If A is anything greater than 3, it is impossible to get our difference of 17. So then, as it turns out, actually, A equals 3 is the bare minimum we need to just barely get inside this bound. If we add A equals 3, we get our total A plus 14D as 241, just barely satisfying the lower bound. And now we can see why this is a unique solution. We are just barely able to squeeze ourselves in there. And if we were to try D equals 16, it's pretty obvious we would miss by a long shot. If we try D equals 16, 14 times 16, we get a total of 224. We can't even reach that even if we set A equal to 10. So we're already out of the bounds. So clearly, this is our unique solution. A equals 3, D equals 17. So our first term is 3. We would add 17, 20, we go up 37, and then we reach 241. And this is our sequence. And remember, what it's asking for is the sum of the digits of A14. And the fastest way to get it is, well, we've already calculated the value of A15 to be 241. So we just have to subtract D one time, 17, to get our value of A14, which we get as 224. And just adding the digits together, we get 2 plus 2 plus